Hello everybody. Chapter 5, which is the beginning of integrals. Most of this you'll find is a repeat of things you have had in the past. So just a real quick intuitive conversation here. So if I'm reading off this slide and it says a object is moving at a constant rate. So this is the picture. Oops. Get in the zone here and get my pen going. So this is the picture of question about the rate. So the velocity is constant, never changing, and distance equals rate times time. So if we draw the graph of the velocity function, which is constant, then the area underneath this curve, due to distance equals rate times time, is 4 seconds, velocity 3 feet per second, the seconds cancel, and you get 12. So this is beautiful, very nice, and this works simply with constant functions, but it also works when functions are not constant. So for this one, if the velocity is not constant, you might have a function that's the velocity equals 1/8 t squared plus 1. Well, I know that's a parabola. And on a regular sketch of a graph, whoops, I know that the y-intercept, if I plug in 0, is 1, and I know it's a parabola. I don't really know how thin it is, something like this. But the velocity, if it's not constant, the area under the curve, if I went to like 4 seconds again, is still going to make sense intuitively that it's the area of this object. Unfortunately, or this little region here, unfortunately we have area formulas for things like this. We could do a trapezoid. And on the last one we had areas of rectangles. But how do we do an area when you have a curved object like that? Well, that is the challenge. So for this problem here, one of the first methods I'm going to tell you, which might be familiar from the past years, is called rectangular method. I'm going to call it a RAM, rectangular approximation method. There are 3 of them. There is a left side rectangular approximation method, LRAM. There is a right side, and there is a middle side, LRAM, RRAM, and MRAM. So if you do look at the picture up here, and you look at all of these rectangles, which corner of the rectangle is touching the graph? It happens to be the left side. This is a visual of an LRAM. So what do? You find areas of geometric shapes that you can calculate, and in this case, it happens to be the left side of the rectangle. So this rectangle here is length times width. That's how you get this area. So the width in this case, because there's 4 rectangles and it goes to 4, the width is really nice. The width is just going to be 1. But how do I get that length? Or the height, if you want to call it that? Well, in this case, that L, the length, it looks like it goes right up to 1, but mathematically, how do I get that? I find V of 0. So I substitute a 0 in there. 0 squared is 0. 0 times 1/8 is 0. 0 plus 1 is 1. It equals 1. So then this is going to be 1 times 1. This guy is 1 and 1/8. Because the width again is 1, but this height on the left side is V of 1. So if I substitute a 1 in for t, I get 1/8 times 1 squared, which is 1/8, plus 1, which is 1 and 1/8. Multiply that by 1, you get 1 and 1/8. And likewise, this height is V of 2, or f of 2 if this is an f function, and this one is v of 3. So notice how I'm using f of 0, f of 1, f of 2, f of 3 to get the heights of those rectangles, those 4 rectangles, on a left-hand rectangular approximation method. And then all I'd have to do is add those up. So as I add those up, I get an answer of 5.75. Okay, so you can certainly use decimals, you can use fractions, you get common denominators, you can really do whatever you want. But that gives me the area of these 1, 2, 3, 4 rectangles. Now, is that a great answer? No, because you have missing pieces here. So if you kind of like take a look at it, it's definitely underestimating my total distance traveled. Why am I saying total distance traveled? Because remember, this would be velocity, so this units over here would be like feet per second. And if these were seconds, when you find the area of one rectangle, you multiply seconds times feet per second, meters per second, miles per hour, whatever you want to do, and your answer is feet. But once again, it's 5.75. That's too low for this LRAM. So I could do an RRAM. So this above is an RRAM. So notice how the rectangle heights happen at the right side of each rectangle. So I could do the width of each rectangle, which I'm going to call delta x or delta t, which in this case is 1, and multiply that by the height on the right side, which is, I'm going to use f, but I could use v, f of 1, plus delta x, which is 1, times f of 2. That's a 2. Plus delta x times f of 3, plus delta x times f of 4, and this little function notation is going to be very common on the answer keys. Notice how that last answer was 7.75. So now another approach would be to touch the midpoint. So I had 5.75 and 7.75 or whatever those last two answers was. The midpoint's definitely more challenging because the height of each rectangle comes between 0 and 1. So once again, you do delta x or delta t, which in this case is 1. It's not always 1. And you multiply that by, in this case, this is weird, f of 1/2. And then you would do the same. How do I find the height of this rectangle right here? This would be f of 1.5. This one was be f of 2.5. And by the way, it's not that complicated. How do you get these values? You just substitute 1.5 in for t, and in this case, you'd have to use a calculator. Now, what happens with these, in this case, it's an MRAM again. What happens if I decide to just not do 4 in an interval from 0 to 4? What happens if I do 8? Well, when I do 8, you can kind of see these little missing pieces have an over and an under with a midpoint, but notice how these pieces are smaller. So what do I want to do with these rectangles? I bet if I cut them in half again, and instead of doing not 4, not 8, but like 16, I bet these little pieces up here would be even smaller. So the plan is to make sure that you try to make as many rectangles as possible if you want a perfect answer. The math becomes mildly complicated, but it's not too bad. Now, I do want you to look at this here in terms of, I'm going to erase all this for a second. In terms of what happens with this delta x now, which is the width of each rectangle. Notice how each of these is a half. So this width is 1/2, and this height of the first one is not f of 1, it's not f of half, it's between 0 and half, it's f of 1/4. So that's what I would be substituting in there. Now they use decimals here, which is perfectly fine. And you add all these up and you can still get an area. Wow, look at that, 6.65. So I can't remember the exact answers, but I think I started with 5.75. oops, 7.5. That was too low. Then I went to 7.75 because those were right hands and those were all above. Then I went to the midpoint, and now when I do 8, I get 6.65. I wonder what the perfect area is if I was able to do like 1,000,000,000 rectangles or a trillion or infinite. I don't know. We'll find out. Now, a couple quick little comments. Inscribed and circumscribed rectangles. There's just some vocabulary here. Sometimes the rectangles, if you look here, are underneath, and sometimes the rectangles, if you look here, are above. I wonder how you figure out if you're over or you're under. Well, let's see. Is this an LRAM or an MRAM or an RRAM? That's an LRAM, right? So an LRAM on an increasing function is under, missing pieces. A RRAM on an increasing function is over. There's some rules in here with over or under, and it has to do with increasing, decreasing. We'll talk a lot more about that later. All right. Exact area, we could do that if we had maybe like a computer program or something that we could add 1,000,000 rectangles and come up with a lot of rectangles. And there are programs on the TI calculators that run that. We'll talk more about that later. Now, for this one, I guess my suggestion is to pause the video and to attempt to do a simple function, y equals x squared, from 0 to 3, and then here's some language you have to get a hold of. It's 3 subrectangles. So it's pretty easy. So 3 subrectangles, try to do it all 3 ways, so an LRAM, an RRAM, and an MRAM. Feel free to pause. I have the answer on the next slide, and then you can check your work after you do it to see if you can crank those out relatively fast. Okay, hopefully we're back. I have the visual, and the question is, how did you do? So an LRAM is 5. An RRAM gives you 14, and an MRAM gives you 8.75. Okay? So notice how those heights are in red here. You probably should have done the same thing. And the widths of the rectangles, I made this easy. They're 1s, so you can kind of see all the work up here. The thing I do want you to notice is that LRAMs and RRAMs are very quick, very imprecise estimates. An MRAM is kind of quick too. It takes a little bit more calculations to figure out those halfway points, but it definitely is a better predictor because this missing part and this part that's over don't exactly cancel each other out, but it's close. I just want to have a quick discussion about speed for your next AP packet. And if I'm going 20 feet per second and my acceleration is 5 feet per second, well, what does that mean? So if my acceleration is 5 and I'm going 20, then the next time I increase by 5 feet per second. So I'm going 25. And then at 2, I'm going another 5 feet per second because that's a rate of change of the velocity. I'm going 30. And what happens if I'm going negative velocity? And my acceleration is still positive 5. The next time I'm going negative 15. I add 5. And then I add 5. Now let's look at the speeds. Speeds are absolute value of velocity. So speeds are 20, 25, 30 here. But the speeds here are 20, 15, 10. So this is speeding up where this is slowing down even though the acceleration is positive. Physics people, you know where I'm going. What about when the acceleration is negative? Well, if your first velocity is 20, then at the next moment you're taking away 5 from that, you're going 15. And then you're going 10. Notice how the speed goes down. Just flip the signs to positive, absolute value, it's going down. Well, this one, if your acceleration is negative 5, next time you take away negative 5 from negative 20, you get negative 25, negative 30. What is my speed here? 20, 25, and 30. This speed's going up as I progress in time. So let me change colors here. Speed goes up. Speed go up. Speed go up. Green. Speed go down. Speed go down. What's the similarities between them? Acceleration is positive, velocity is positive, speed go up. Acceleration is negative, velocity is negative, speed goes up. If they're different signs, speed go down. So that's a very important fact to understand. If velocity and acceleration are the same sign, speed goes up. If velocity and acceleration are different signs, speed goes down. Remember that if you're ever asking for if the speed is being increasing or decreasing, it depends on both velocity and acceleration. Most people do a mistake by only looking at the acceleration. The last thing I have to tell you leads you into kind of like your homework. When you get to your next homework assignment, it's going to ask you to fill in a chart here on number 7. And that is they want you to do an LRAM with 500 rectangles. So yes, that's right. You need to do 500 length times widths. However, there is a program in your calculator that does that very fast. However, it's really cool. It's really nice. But the AP graders know that your calculators do this very fast. So they usually put these on the no calculator part. This question, number 7, is not a great AP question, but I want you to practice doing this through a program on your calculator because I want to see the limit of these things as the number of rectangles gets increasingly larger to develop the understanding of the formula for a definite integral. So when you get to this question 7, I am probably going to post a video on Canvas or show you in class on how to do this manually using a calculator, and that's what you would do for number 7. Thanks for listening. Definite integrals, away we go.